Last time, we began our study of the one electron, or so-called hydrogenic atoms, where we have a nucleus and an electron, the electron with its mass lowercase m and charge minus the fundamental charge, and the nucleus, which has a much heavier mass, much greater than the electron mass, which then had a charge which is positive some integer number of nucleons, the atomic number z, times the fundamental charge. Now, we had quickly looked at this system. It was bringing us back to the Empedoclean description of the universe around us. We realized we had to contend at least with the fact that we were in 3 dimensions. We showed how to quantize such systems. It was a rather rapid and intuitive process. We realized we would need now a wave function that's a function of 3 dimensions, whose modulo squared then would be giving us the probability density for finding the electron. We then decided what our operators would be. X, Y, and Z operators are just the corresponding coordinate values of the electron, and the corresponding momenta, based on the de Broglie hypothesis for a traveling wave, was simply that the corresponding momenta operators are h bar divided by I times the derivative with respect to the corresponding coordinate. Putting all that together then, we wrote down the time-independent Schrodinger equation in its usual form. We're now looking for these bound states, and these solutions I'm going to be calling capital psi instead of capital phi for the pure states of energy. I won't be using capital phi anymore because I actually need phi for a lot of different things, and I'm going to begin to run out of Greek variables, as you will see coming up in a moment. In any event, this will then be the wave function as we write it down. Finally, then, inserting these operator definitions into the Hamiltonian associated with the system, we came to the following form of the Hamiltonian: minus h bar squared on 2m times the sum of the squares of each of the different derivative operators minus the charge on the nucleus times Coulomb's constant times the square of the fundamental charge times 1 then over the distance of the electron at coordinates x, y, and z, which would then be the square root of the corresponding Pythagorean distance. Very good. Now, before we proceed to finding methods to attack the complexities that we see here in 3 dimensions, I'd just like to mention a little bit of shorthand that will make our lives a little bit easier as we move along. The sum of these 3 different derivative operators, of course, is a well-known operator. This is the Laplacian operator. We will abbreviate it in the standard way as del squared. Another way of thinking of this Laplacian operator, of course, is that it is the divergence of the gradient operator applied to our function. The other thing to notice is that this square root of the coordinates that correspond to our operators, of course, simply represents the distance of the electron to the nucleus. We had called that r, so we may as well just refer to that square root in a shorthand as r, but if we need to know what it's composed of, we have its full definition here. Very good. So from this point on now, we're going to begin to think about how we can analyze the complexities that we see in a system such as this.